the NP versus P problem is one of the most important, is the most important problem in computer science, and arguably, and probably also one of the most, if not the most important open problems that has been argued in mathematics. It's a millennium problem of the Clay Institute. Who solves this problem gets $1 million. And we have here Lance Fortnow, who is one of the world's best-known experts on computational complexity, and in particular on the NP versus P problem. So he has his doctorate from the MIT, and he held various faculty positions at the University of Chicago, where he also was a presidential NSF presidential faculty fellow at Northwestern University. And last year he moved to the Georgia Tech, the Georgia Institute of Technology, where he moved there as a chair of this institution, the computer science department. He has made truly fundamental contributions to theoretical computer science. For example, celebrated results on interactive proof systems, on time, and he has given time-space lower bounds for satisfiability. He dealt with de-randomization, how can you transform a randomized algorithm into a classical algorithm. He dealt with oracle machines and sparse languages, and all this has to do with the NP versus P problem in a certain way. For this work, he was elected Fellow of the ACM, of the Association of Computing Machinery, in 2007. He also worked on other areas like quantum computing, genome sequencing, economics, microeconomics, game theory, both complexity and strategy design for game theory. But he has also done much for dissemination and outreach. For instance, he co-founded with Bill Gazzard one of the first blogs on computational complexity, which is now one of the most important, most read blogs in computer science and theoretical computer science. He has written a survey paper, I think with the same or similar title. It's not the same title, but very much related to the present talk. It's called the Status of the P versus NP Problem, which is currently the most downloaded article from the flagship journal in computer science, which is CACM, Communications of the ACM. And he has also very recently published a fantastic popular science book, and I show it here. It's called The Golden Ticket, NP and the Search for the Impossible. And it's also on display outside of this room. And well, why the title The Golden Ticket? Because in this book, Lance shows that actually, if you solve the P equals NP problem, you can solve many other problems, all other problems of the Clay Institute, all other millennium problems. That actually gives you, instead of 1 million, it gives you 6 million. These are the 6 million. I don't know if you have to pay taxes on it. So Lance, thanks very much for coming, and we are looking forward to it.
Thanks for that, not quite true. Very, very well, wonderful introduction. Thanks for the Clay Institute for organizing this week. It's a great week. We've had a great workshop, and inviting me here. So I'm very happy to be here. So Dina, going to talk about the P versus NP problem. I'm going to go back a couple years. August 16, 2010, New York Times, major newspaper in the U.S., and had this kind of interesting article. Step 1, post elusive proofs. Step 2, watch fireworks. That was the title of the article. And some of you might remember this. Vinay Dialekar, a mathematician, electrical engineer, Hewlett-Packard, posted a proposed proof of what is known as the P versus NP problem on a website. He quietly notified a number of P researchers. In fact, he did send a message to 22 people. I am pleased to announce the proof that P is not equal to NP, which is attached in 12.1. It turns out I still get asked, so let me make it clear that the Dialekar's proof didn't actually work. The problem's still wide open. We'll get to the problem in a second. But the fact that it's sort of that, we have lots of these, and I'm sure it's true for all the millennium problems. You get lots of these purported proofs that come in. But for some reason, this one got a bit more traction, and there was a huge amount of excitement that went on for a week or so until it was clearly shown that this proof was not going to succeed. And the fact that, and in fact, I think that it really sort of shows what's the real excitement in this P versus NP problem. So if you look at it, how it stands among the Clay math, the Clay, the Millennium Prizes, it sort of stands out, for one reason, it's the only one that's not named after someone. But it also is, in some sense, I think, one of the more accessible ones, in the sense that I think it's a bit sort of easier to explain to a lay audience than most of the other questions on most of the other Millennium Prize questions. So to give an example of this, I'm just going to go through a couple slides that I've used for more of a general audience talk to try to explain what the P versus NP problem is. Just imagine a world I call friendly, where everyone's are either friends or enemies. Bella could be friends with, now we get it backwards, Jacob, or Edward. Yeah, I chose these characters because they work for high school. But you not know these people, they depends on Anyway, you can be friends with Jacob, friends with Edward, but they may not be friends with each other. You can have any kind of sort of friendship or not. And there's this world they call friendly, where everyone's are friends and enemies, and so you can imagine a graph of all these people, and just these lines represent the ones that are friends with each other. And then you can kind of start with this, and you can start asking, well, what about questions about this? And one thing you might want to do, for example, is to see if you can do it like a dating service. Can I match up the woman with the men? And so that everyone gets matched up with their friends. And you can look at this for a second, and you can see that in fact it can be done. But you can imagine that if I didn't have 4 and 4, there's only 4 and 4, there's only 24 possibilities of matching them up. But you can imagine having 1,000 and 1,000, and then the number of possibilities is humongous. Far more than you could possibly search on a computer now or ever in the future. So, but yet, nevertheless, despite the fact that there are all these very many possible ways to match people up, and it'll be too hard to go through all of them, there's still algorithms that lets us match them up efficiently. And actually, it's a rather simple algorithm. You start off just by being a little greedy. So you match these two, then these two, then these two. Now it looks like you're stuck because there's no no extra matches these. But what you can do is that there's a path. There's a path of unmatched and matched edges that go from one to the other like this. And if you just flip the path, and then you have a match. And in fact, that's called an augmenting path. And in fact, what you do is you keep just kind of searching for those kinds of paths, and then flipping, and that gets you one more match. And you do this until you get stuck. And then there's actually theorems out there that says if there really is a match, you won't get stuck until you match them. So in this case, in a dating service, there are efficient ways to find a matching of everyone involved. And in fact, we can do this. We can do this efficiently. We can have millions of men and millions of women. In fact, this actually gets done, for example, on a different form when they match residencies with medical schools. So actually, we're really out in the top. We can do this. And we have a name for the kinds of problems we can solve efficiently, and that's what we call the P. Let's look at a different kind of problem. I want to now look at cliques. Clique is just a group of people who, all of whom, are friends with each other. So again, here's a clique of size 3. So, it makes sense. It even makes sense in Facebook. You take Facebook, you can look at what's the largest number of people, all of whom know each other in Facebook. Actually, I don't know. The question is not only do I not know, but if I worked with Facebook and I accessed all their data, I still wouldn't know. Anyway, here's a clique of size 3. Can you find a clique of size 4? You're all mathematicians here. I mean, it's actually not that hard to find. There is a clique of size 4. People, you spend a couple minutes, you see that. In fact, there are 4 people, all who are connected to each other. But you can kind of see it's a more difficult problem. And in fact, we don't have algorithms that will find cliques, find the largest possible clique. Particularly, we don't know of it. And so as far as we know, clique in fact is a problem where the solution is in fact hard to find. But it's easy to verify. If I gave you the solution, it's very easy to check. All the, if I said, here's a clique of size 4, you can check that. Yeah, these look, they're all connected. There's a clique of size 4. So it's easy to check. If I say there's a clique of size of at least 100, I can give you 100 people. You can check that they're all connected. But trying to find them might be very difficult. Again, the number of possible cliques is humongous. And so clique is a problem that's efficiently verifiable. We can check a solution. This is what we call NP. P, easy to solve. NP, easy to verify. If they're equal, then everything that we can verify quickly, we can solve quickly by cliques. If they're not equal, then there are some problems we can verify quickly that we can't solve quickly. And then the NP question is just asking, is that true? Is everything problem that where we can verify solution quickly, can we also solve it quickly? I don't know. I think that the general consensus is the answer is no, but that's it. Now, of course, that's kind of a general. I'm going to tell you what efficient means, for example. But that's just it is the kind of problem that I can just spend a couple of slides and explain to a general audience. I think that makes it sort of a little more, it's kind of a different sort of problem than the other ones in this slide. So, as I was saying in the introduction, in fact, I've done a bunch of writing I've been asked to do some writing on the PNP problem. First as an article for computer scientists, and then as a popular science book. And the one thing that you kind of have to do is you step back. So when I go to conferences and we write scientific papers, we tend to be very deep in the field and dealing with a lot of the technicalities of the P versus NP related problems. But when we actually start writing about these things, it kind of forces you to step back and start to think about what is this problem really about? Why do we care? Why is it such an important problem? Why do we see it come up in lots of different disciplines? And I really think that there's actually 2 problems here. And I think we sometimes miss this. First, there's a very mathematical problem. It is among all other things, it really is a well-formulated mathematical question. Does P equal NP? And it still would be, incredibly wonderful and, worth well more than $1 million if we could find a solution to the problem. But there's also just a general problem. It's a general issue of finding of what's the power efficient computation. What can we solve with computers? And so we just, and the more informal definition, I think, it really hits on it. Can we efficiently solve all the problems with efficient solutions? How in the world, why is P equals NP important? What would actually happen if P equals NP? And P equals NP in an intuitive way, not necessarily a mathematical way. And then, but then of course, we don't think P equals NP, so if P doesn't equal NP, how do we deal with those issues? How do we still, solve the problems we need to solve? And so I want to kind of hit on both of these issues, both the mathematical and also kind of this broader view of what is the P versus NP problem? Why is it important? Why do people, why does it really seem to matter? Let's start off with the mathematical. And the mathematical starts with, in order I want to talk about efficient computation, first you have to talk about computation. And to talk about computation, some of my favorite model of computation is one of the first ones, Turing's machine. He created this idea in 1935 of just an extremely simple device that basically it's a device that has this infinitely long tape and with a little bit of with each tape storing a handful of characters maybe, and all it can do is move the tape left or right and take the current character and replace it with another character. That's all it can do, and yet it captures all of computation. That's a pretty amazing thing. How do we formally, this is just a picture, how do you formally define a Turing machine? Well, you have to define the various pieces. You have some sort of input that you can, something like binary, where you can describe the problem you want to have. You have some blank symbol to distinguish emptiness in the tape. You have a tape alphabet with sort of extra characters you can write on the tape. You have some sort of finite memory that handles the control with some finite number of states and some special state that says say yes, and probably some other state that says no, and put that in. And then your computer program itself, which we encode with a transition function. And what is a transition function? It's pretty safe. You look at your current state of memory, you look what's under the tape head, and then you move to a new state of memory. You write down something, you write down some symbol on the tape, and then you move the tape left or right one square. That's it. That's the entire Turing machine. And then from this Turing machine, you can, I'm not going to go through the formal definition. You define some notion of induction. Define some, you have some sort of initial configuration. You run the Turing machine, and then you say this machine accepts if it ends up in the accept state. And the Turing machine may not accept. Maybe it rejects. Maybe it runs forever. It's a wonderful theory. I hope that there's this beautiful theory of computation that's generated from this very simple device in this Turing machine. There are lots of variations of Turing machines. The one that we're going to care about is the non-deterministic Turing machine. So a transition function gives you, this transition function as I wrote it, gives you one possibility for the next step. A non-deterministic machine might have many possibilities for the next step. So instead of going to one triple, say simple direction, maybe it goes to multiple triples. And then it can non-deterministically, non-determinism is, think of it more as an existential. So it's sort of, it gets to sort of magically choose the best possible choice that gives it the best chance of reaching the accept state. That's I think the easiest way to do non-determinism. Okay, so now we can define efficient computations. N here represents the size of the problem you want to solve. And then we can define these, what we call classes of languages. Yeah, I can get from the beginning, yes. Classes of languages, classes of problems. D time for deterministic time instead of machines accepted by deterministic Turing machines that runs in time t of n, where t is some reasonable function, and non-deterministic time t of n is the same thing for non-deterministic Turing machines. Then you can define p. P, now we're going to understand what the letters stand for. Okay, I hate the letters PMP, the PMP problem, because it's not very, these letters are derived from this formal definitions of complexity. So you can see that P stands for polynomial. It's the polynomial time. It's the union polynomial time. P is non-deterministic polynomial time. So you can see that the letters actually do have some connection to the problem itself, but if you're trying to explain it to a physicist and they say, I always thought NP means not polynomial. And no, that's not what it means. But actually, that's not a bad way to look at it. So, and then the question is, the PMP problem is, here's that formal definition, non-deterministic, deterministic polynomial time, non-deterministic polynomial time, and then does P equal NP. Now, the difference between non-deterministic polynomial time means that you can make these possible choices. So you could solve a problem like clique by non-deterministically using your non-deterministic choices to guess a potential set of vertices of maybe, say, size 100, and then in deterministic time, you can check that solution actually, that those choices actually check all the edges between them, that actually gave you a large clue. A couple of things that really make this. First of all, I mean, if this definition changed, depending on the model of Turing machine, then it would be a very good definition. But the beauty of this is that it doesn't. It's very robust. If I have many tapes, if I have a random access Turing machine where you can address a large amount of memory, you can find it in a reasonable way. But I look at other models of computation like the lambda calculus, or take your favorite programming language, C++. That's a defined non-deterministic version of that. But you look at C++, or even, you can even use, it turns out even like LaTeX has a programming language built into it. You can define PNP using any of these things, and it's exactly the same problem. The same class P, the same class NP, and the P versus NP problem doesn't change. I just want to say a little bit of a caveat that if you start allowing your machine to flip coins or use quantum mechanics, then you may get different. You might not get the same classes. This PNP problem doesn't directly talk about probabilistic quantum machines, but for all this kind of standard computing models that we actually use, it's really robust for those. The other very important part about PNP problems is the notion of hardness, of reduction. So reduction is simply having some computationally efficient process. You have a problem you have a problem A, you have a problem B, and you want to, in some sense, reduce problem A to problem B. So you have some very computationally efficient polynomial time algorithm that takes inputs that are in A, reduces them to problems in B, and things not in A, that reduces them to problems not in B. And what does that do for you? That means that if I had some algorithm, some efficient algorithm that could solve B, that would give me an efficient algorithm to solve A. I could just use B as a subroutine. Use that algorithm for B as a subroutine. And so if A reduces to B in this way, then in some sense B is harder than A, and A is easier than B. The other way, the positive, is also true of A. There's no argument for A, and there's no argument for B. So that gives us a notion of relative hardness. But then it lets us ask questions like, are there hardest problems for NP? And in fact, they are, and they're called the anticomplete problems. The first of these was done independently by Steve Cook and Lena Levin back in the early 70s. Boolean formula satisfiability. This is just, you take a logical formula and you just ask, is there a way to set the variables true or false, make the formula true? Very simple question. Turns out to be NP complete, as hard as any other NP problem. And then, within a couple of years, a whole slew of other problems also seem to have this property. The clique problem that I mentioned before, the traveling salesman problem, where you want to visit a large number of cities in some order. Doesn't matter what order you go in, but you want to minimize the number of miles that you take. Map coloring. You probably all heard of the 4-color theorem that says every map can be colored with 4 colors, so that no bordering state share the same color. But whether or not a map can be colored with 3 colors, that also turns out to be NP complete, as hard as any other problem in NP. There was something with biology. It's basically just finding the shortest sequence consistent with a bunch of other sequences, something used for DNA sequencing. Playing large Sudoku games. Lots and there's thousands and thousands of other ones. Problems. Now, what does this NP complete mean? It means several things. It means that if I can solve any of these problems, they're all reducible. Every NP problem is reducible to each of these, so particularly reducible to each other. If I can solve any of these problems efficiently, I can solve them all efficiently. And P equals NP. So P equals NP is exactly the question for any one of them, or for all of them, whether there's an efficient solution to any of these problems. So that's what really makes the P versus NP problem important, is that it not only just captured this mathematical idea of efficient computation, but in fact captures a large number of combinatorial problems people actually were caring about even before this problem was formulated. So let me just do a very quick History of P and NP. When is the back, Turing had his machine in 35. I think a big conceptual breakthrough came in 62 when Hardness and Stearns, Urs Hardness and Richard Stearns, was trying to get a notion trying to capture some notion of efficient computations, and had the idea that computation time should depend as a function on the size of the problem you wanted to solve. Wasn't that it was one of just kind of beautiful insights. It really let us be able to define what a real notion of what it means to compute efficiently. And in fact, their paper on the computational complexity of algorithms is what sort of named our field computational complexity. In '66, Jack Edmonds and Alan Cobham in separate papers talked about what would be the right notion of efficient computation. They're both mentioned, though not necessarily saying this is what it ought to be. Polynomial time as the notion of efficient computation. That's where we got sort of the class of P came from the model of the newspapers. And in 1971, Steve Cook on the US side defined the first empirical problem, sort of setting up, basically establishing the P versus NP problem. And I just want to I wanted actually, Steve Cook is actually here. So I'm the founder of the P versus NP problem. And then in 72, a year later, Jacob showed that a whole number of common problems were anticipated and then just set up an explosion. He was mentioning 11 did similar work on the other side of the iron curve, things were separated back then. In 79, there was this wonderful book by Gary Johnson whose second half of the book lists hundreds and hundreds of anticomplete problems. Still a great reference book, one of the best books that computer scientists should own. And then, just thousands of anticomplete problems over many disciplines have been discovered since then. So it's really become a burgeoning field. Okay, so let me do a little detour and talk a little bit about, I think, this kind of outside view of what does the P versus NP problem do. I mean, what happens at P equals NP? We cure cancer. I'm not be bold here. P equals NP, and I mean P equals NP in the you're mathematicians, so if people kind of say, you can have P equals NP with the definitions the way they are, but if you have an n to the 50 time running time for stat, it's not going to be that useful, and that's true. So think here when they say P equals NP as being something like, there really is a truly efficient algorithm for any complete puzzle. That could be true, we don't know. It's not true. And then if that's true, we can actually do incredible things. We can cure diseases. Why? Let me try to argue why. Again, there's no proof here, okay? Because how do you prove that a mathematical theorem gives you cure for cancer? But I give you arguments. Okay, so you're not a biologist, so but you can sort of get the idea. You have some sort of cancer attaching to your membrane here, and what you want to do is create a protein that will come and sort of starve off the cancer cell without affecting the rest of the cells in your body. It's the basic idea. You want something that attacks cancer cells, the cancer cells in your body, without attacking the rest of your cells in your body. And in order to do that, you kind of have to create a protein with the right shape that will interact with the cancer cell in one way and interact with the rest of your normal cells in a different way. Now, there's a process that somehow converts some sort of DNA sequence into a protein shape. Now, we don't even understand the forward reference process. I mean, we don't even understand how the DNA sequence ends up in a protein shape. I mean, there's been some research on it, but no one really understands this process. But if P equals NP, what do you think? P equals NP, I mean, this is some computational process. If P equals NP, we can sort of try many possibilities for what that process could be and find a short one that kind of matches what actually happened from the DNA sequence to the protein. And then once you actually know the process is moving forward, you can then invert it, again, using P equals NP. Using P equals NP, you can then invert that process you figure out what shape you need, which of course you equals NP to find out what shape you need, and then you can then invert the process, come up with the right DNA sequence that then creates the protein that attacks the cancer cells with the rest of your cell alone, thus eliminating, and you would actually be able to tailor this for different individuals. You take you figure out what kind of cancer they have, you also look at their own DNA to see what kind of their cells are, and you're actually able to actually tailor it for individual people, and this will cure cancer. And now, of course, no one will ever prove me wrong because I don't think P equals empty. But the argument's based in sound, and if you do talk to biologists, the real issues in biology are computational. They're really hitting upon hard computational questions like, protein folding, and P equals empty would, if it was efficient, would settle those questions. So P equals empty really, can do a number of dramatic things. A lot of it comes from this idea of Occam's razor. Occam's razor, he was an Englishman shifting fire from the 14th century, and he, I'm a Briton, so you probably all know Latin, so I won't even try to pronounce it. But basically it means entities must not be multiplied beyond necessity, or like if it is the simplest explanation is usually the best. There's actually some mathematical intuition as to why this Occam's razor is actually true. But just because the problem though is of course trying to find the simplest explanation. Well, actually, let me give it. But if P equals empty, you should find the simplest explanation. So there's the usual example of the Rosetta Stone, which was used to find the simple grammar that would convert. You were able to help us. This was the stone that had a decree in various languages, in which was a way used to find a way to actually learn how to read hieroglyphics. And a place to see it a lot is in a very budding area of computer science known as machine learning. Machine learning is the idea of just using statistical ideas to try to sort of learn the algorithms and then be able to use them for a variety of purposes. Just look at Google alone. They seem to be the masters of this. They use machine learning for language translation, voice recognition, facial recognition, and even cars that drive themselves. And the beauty here of what Google does is these are, or actually what this happens in the machine learning community, I should just say Google, is that they're all these ideas, these very different things that are done are basically done with the same basic algorithms, the same basic ideas are being used to come up with tools and come up with the basic, learning the same basic algorithms that are powering these very different applications. So, if P equals NP, you can do lots of amazing things. This is a robotic hand that comes out of the University of Washington. It's a wonderful mechanical device. It has all the range of motion of a human hand, but it can't do very much because it's just too complicated. But if P equals NP, you can actually make it do anything a hand could do. Like play a piano, for example, or even or even compose, pieces. Again, you can kind of use it in biology to cure diseases and among other things. This is just a real picture of a baseball game, but if P equals empty, you could actually create virtual reality that looks the same as real reality. That can make it impossible to tell the difference. You could actually create new works of art. Could creativity be automated? If you give a bunch of examples, you use P equals NP to find the algorithm that Schubert used for composing. Could you finish his unfinished symphony? And then the worst one, remember the movie Wall-E, where everything was automated and people were just sitting around doing nothing all day. Probably the worst side effect of P equals NP is you can basically automate anything. And including all of us. And give us, basically, well, they live in this wonderful world, but we wouldn't really be needed it. Well, we don't think P equals NP. So, what happens if P doesn't equal NP? And there's actually some good things that come out of P not being NP. One is cryptography. For example, when you use your bank, this is the U.S. bank, and you see this little lock, you know that when you type in your user ID and password, this is actually a way that you can communicate to your bank your username and your password in a way that no one listening in on the internet with a Wi-Fi signal or whatever will be able to figure out what the username and the password is. I don't know, start getting some NSA jokes. Besides that, no. The neat thing is that you can actually do this using something called public cryptography, even though you never actually, you and a bank have never physically met. You've never actually sat down and exchanged keys. The public key cryptography actually gives a way for us to do this, even though we've never met before. You're still able to communicate over an open internet and still have your information safeguarded. And that's only possible. I mean, you need more than just P not equal NP. You need some additional assumptions. But if P equals NP, you can't do this. And then kind of a really neat thing. This is a work of Goldwright, McCauley, and Richardson back in the 80s, something called zero knowledge proof. And I think it's best done with described as Sudoku. So you probably know the Sudoku game. The goal is to fill up every row, column, and square with the numbers 1 through 9. So that one number appears in each place. So imagine you're working on a Sudoku problem and you can't find a solution, and then you're convinced that in fact there is no solution, but your friend knows the solution. Now your friend can convince you there is a solution by actually giving it to you, and then you can check that it's a solution. I mean, this is an NP problem. But that's not very, that ruins it for you, right? Okay, you check the solution, well, now you don't want to solve it anymore. But the beauty of zero knowledge proofs is actually a way that I can convince you that there is a solution even without revealing anything more than without revealing the solution itself. Or in fact, revealing anything about the solution other than it exists. And that's a beautiful work. I won't go through here, but by those 98 zero knowledge proofs. A wonderful thing. There's lots of neat things you can do with 69. So the next thing that comes up is how do you deal with NP problems? So the real world is, in the real world, this beautiful world I talked about, P equals NP. But the reality is, no, it's not going to be the case that P equals NP. Or if it is, as long as we don't have arguments for NP complete problems, it's essentially we're in this world where P doesn't equal NP. But we still have these problems. And complexity theorists, we kind of think of, well, okay, it's NP complete. Okay, it can't be solved, but people really do have to solve these hard problems. So I think what P and NP tells us is that you can see these problems, you can see they're NP complete, and then you can say, okay, I'm not going to find an algorithm that's always going to work all the time. That's just not going to happen because we don't believe P equals NP. You're just not going. You're just not going to come up with that. Don't even try. But doesn't mean that you can't try to do something. So, how do people deal with hard problems? And I think there's a whole lot of different ways. One is brute force. Right, so in 1971, when Steve came up with the P versus NP problem, it was also the same year as the first microprocessor, the Intel chip. And it was slow. Those computers back then were really slow. When I was a kid, they would say, if you want a second delay on your computer, write a loop to go to 536. That was computers were really slow. Computers have gotten a lot faster since then. Just so, the point is now you can do a trillion operations in a second. Look at a trillion operations, you could just, in trillion operations, you could solve a stat problem of size like 30 or 40, and just by trying all the possibilities. So you can solve, you actually can do quite a lot you actually solve medium-sized problems just by being stupid, just by trying all the possibilities if they're not that big. If they're a little bit bigger, you have to be a little more clever, so you can cut down the search space with some more cleverness, and you can solve even much larger problems. So basically 100 variable satisfiability questions, mostly you can just solve them. Heuristics are algorithms that work most of the time, but not necessarily all the time. And so there are quite a few out there for satisfiability, for traveling salesmen. You can solve satisfiability often on 1 million variables. Not all the time, but often sometimes you can. Or traveling salesmen on 10 or 20,000 cities, things like this. You can really, you can actually solve them in real world cases that you care about. Not all the time, not all the real world cases, but quite often. There's an area called fixed parameter tractability, parameterized complexity, where you look at problems with small parameters. You have the clique you're looking for isn't that big. In some cases, there's different kinds of anticomplete problems where you can even have reasonable size parameters and still be able to solve those kinds of problems. Approximation, so like traveling sales is a good one. Maybe you can't find the absolute shortest route. But you can also find a route which is maybe 5% larger. That's probably good enough. So that might be more tractable than the other possible. So approximation is another way. There's been a lot of work in recent years showing some beautiful approximation results, but actually quite a large number of problems turned out to be hard to approximate, at least in the worst case. So clique, for example, is very difficult. To even come up with not only the largest clique, but anything close to the largest clique in general. Unless people solve a different problem. So this is something that we don't really think about, but often it's not the and P versus NP. I mean, that's not the computational problem you need. You have some tasks you need to solve. This computational problem is something that helps you solve that task. It might be a different computational problem. It gets you to solve the same general task. And so you might want to look at a different kind of problem. And then sometimes you just have to give up. So I can teach people, well, listen, okay. Give up. There's lots of other problems that you can solve. And some things are just intractable. That also happens too. So it's more, the p-not lengthy. It's much more than just saying, the problem is anticomplete. The problem's very hard. The question is, what do you do with it once it's hard? It's just P versus NP is not the end. Anticompleteness is not the end game. That's just the first step. Trying to understand how to solve problems. So, I think P not equal NP. How do we prove P not equal NP? Well, I'm not gonna. If someone said I should use, this would be the perfect place for me now to give you my proof that P not equal NP. I could just receive my $1 million check right now. No, that's not going to happen. So let me not try to tell you how do you prove P not equal NP. Let me kind of explain what doesn't work, or what we tried. So diagonalization. This is sort of like basically similar to Cantor's theorem. It's the best. It's the simplest technique to show that things can't be computed. Basically, you just build a language that you build a problem that you go through every possible machine. Let's say SB all the possible computable languages. Only count a number of computer programs, and then you just diagonalize against them. You actually create a language which, on different inputs, you do something different than what the machine did, and then this is an idea called diagonalization. It's basically the same as Cantor's argument that reals and integers of different sizes, and this is a tool for showing things can't be computed. You just make sure that no machine will actually succeed. So this has been successful in showing that there are things that are not computable. It's been successful in separating P from X exponential time computing, for example. It doesn't seem to work for NP because NP doesn't seem to have enough power to simulate P. You can't, in order to do diagonalization, you have to kind of simulate and do the opposite, and NP doesn't seem to have enough power to do it. There are these things called relativized worlds. I'm not going to get into too much, but basically it kind of shows that sort of a bunch of standard techniques are not going to work. Diagonalization, for example, we say vortex doesn't seem to work with every P from NP. You can get some weaker results using diagonalization. No argument satisfiability that simultaneously uses a small amount of memory and a small amount of time. So this is a far away from PNP. There was a big push in the 80s for using circuit complexity. The idea here is that you can take any polynomial time algorithm and convert it into a polynomial-sized circuit, just ands, ors, not gates, built upon variables. And then the nice thing about circuits is you can kind of just try to take it one gate at a time. By kind of showing that, if you can kind of argue in some sort of measure that no gate changes things very much, then maybe you can argue you need a lot of gates to solve some problem. And in fact, that was actually done successfully, for example, showing there's no monotone circuit that solves cliques, for example. Monotone means no negations. If I don't have any negations, there's no small circuit that will solve clique. So there's a lot of excitement in the 80s that this might lead to a switch of P versus NP problems, but once you start adding negations, then things get very complicated. And we have a lot of nice theorems here, but still, again, nothing really gets that close to P versus NP. It does good. It can get some results if you limit the depth of your circuits, and again, if you don't have negations. And then there's this idea of the school of natural proofs that kind of says kind of a lot of the standard techniques that we use is a limit to what circuits, what kind of tech, some limitations that this technique would be difficult to settle. Proof complexity is another interesting idea. The idea is you take an unsatisfiable problem and you argue that it has to have a long proof of unsatisfiability. If P equals NP, or even if NP is closed in a complement, then every tautology is going to have a short proof that it's really the tautology and unsatisfiability is similar. So you take any tautology, and every tautology is going to have a short proof of being true. And then you try to show that tautologies only have long proofs. And people have great success on certain kinds of proof systems, but like resolution, some more complicated ones. But again, it's still a long way from general proofs that you really need to do to show that NP not equal to 1. Again, this is another nice approach, but still far away from actually selling the P versus NP. So let me end. How am I doing on time? No, good. Let me sort of end by talking a little bit about the future of P and NP, or what lies ahead for I think the P and NP problem. Quantum computing. There's a big excitement all these days about quantum computing. It really does seem like quantum computing, if they're actually built, I'm not a physicist, so I can't really talk about whether or not they'll be built. But if they're actually built, there actually is a belief that they'll go beyond P. In particular, there's this beautiful algorithm by Peter Shor that shows that you can factor numbers efficiently on a quantum computer, which is something we don't believe we can do efficiently on a classical, traditional Turing machine efficiently. But on the other hand, there doesn't seem to be any evidence, in fact, there seems to be evidence against being able to solve general NP-complete problems. There's a nice algorithm by Grover that gets you quadratic speed up, but that's not a very big speed up in these issues. So quantum computing, I think, will help with a certain class of problems. Whether or not they're, first of all, you have to build them. But if you're able to build them, large-scale quantum computers, maybe it'll get some help. Probably not in general for general NP problems. And then you begin to see a rise in cloud computing and multi-core computing. What happened back around 2005 is computers stopped getting faster. power issues just prevented computers from getting having a little transit. You're not able to make your computer faster without melting it. And that happened around 2004, 2005. But Moore's law, you probably heard of Moore's law, which says the number of transitions that you can cram in a certain amount of space on a transistor doubles every year and a half to 2 years. That seems to keep going. So, but the problem is we're no longer able to use that to make computers faster. So what people do instead is they just put more computers on a chip. And that's what multi-core computing is. Or the other thing that we're all seeing quite a bit of, and a very similar style, is cloud computing, where in fact most of the computing you do in your computer isn't done on your computer at all, but done out there in the cloud, on data servers from Google and Facebook and everything out there. And they have tons and tons, rows and rows of machines that are crunching on these computers. So how does that affect the NP problem? Well, it lets you do searching by, especially NP problems, you can break up the search space. And then you could assign the search space to these different computers, and that would help you, do searching better and being able to actually speed up your search for the solution. But again, all this parallelization is limited. Exponential blow-up is still exponential. Exponentials grow really fast, as we suspect, and so while this will help us solve NP problems faster, it's still not going to make NP problems. It's not going to efficiently solve large NP problems just by using multi-core and cloud computers. And then finally, Katan Momole. He's a professor at the University of Chicago. He was actually here earlier this week. He's been working on an algebraic geometry approach to figures of NP problems. There's a lot of questions about whether or not this approach will work, but it's kind of a neat, sort of a fresh idea on trying to tackle the P versus NP problem using a different branch of mathematics. And not that I want to mention that, especially in this context, because maybe the solution to P versus NP won't come from us complexity theory, but really come out of that field from some completely different branch of mathematics. And so maybe an institute like this, which brings different mathematicians together, might be just what we need to try to find a great solution to the problem. Actually, just realize, prove already that the P and P are different. But just one last chance to walk my book. And thanks very much.
Time for quick questions, please take them.
Any questions?
Can I, Peter Neumann from Oxford, can I pin you down a little bit on your optimism?
I'm not optimistic at all.
Well, no, it was a bit cagey that if P equals NP, then we can solve all these problems.
Yes.
My experience from computational group theory is that some of the problems that are polynomial time soluble, the degree of the polynomial is so large that we have great difficulty actually solving them. For example, if we take a couple of matrices of size 2000 over the field of 2 elements, and we ask for even the order of the group that they generate, we can't do it. Is polynomial time too big?
So, I think a couple of things. First of all, I tried to throw a caveat in when I was talking about it, where mathematically the polynomials are large. But actually, group theory is a bit of the exception. In most cases, when we do have algorithms to solve these problems, they tend to be reasonably efficient. So they like the Nash algorithm or linear programming or lots of the other algorithms that are out there. So they often start off with high exponents, but then we tend to get them down. And there are definitely exceptions to that. But I find that, it's sort of like physics. P P is an approximation to efficient computation. It has nice properties. It has it's very robust, closed under subroutines. That's a nice things you want from efficient computation. So it's a nice model of efficient computation, but it obviously doesn't match efficient computation. So we do need to be careful with the P-NP problem that it doesn't exactly match the intuitive idea of the efficient problem, infinitely verifiable is the efficiency. But I think it's a good, in practice, it's been a reasonably good, like I said, some exceptions, particularly in the own field, but in practice, it actually has been a reasonably good measure of what's efficiently true. So I think it's still sort of the right question. I'm still strongly believe it's the right question to ask.
Very good answer. Thank you.
Is it known whether there exists either a proof that P equals NP or a proof that P does not equal NP?
I think that's not true for any mathematical statement where we don't know the proof, where we don't know which way it goes. So no, of course it's possible that it could be independent of whatever theory of logic you want, and then you can go wildly speculate on what that means. You know, what non-standard models of computers, or polynomials, or algorithms, and what's a non-standard. You can get all the puzzle breaking this if you start going down that path. But I honestly, but I don't think, it's also another thing is that the P-versus problem isn't that old. 1971 wasn't that long ago. It's only 42 years old. So I think it's way too early to start saying we've put so much effort into this, we can't do it, therefore it can't be done. Obviously, we've seen other problems get solved after hundreds of years. So I'm still very hopeful. Although I'm getting less hopeful that it's going to happen before, my lifetime. But I'm still hopeful that we'll resolve it. Any other questions? I don't want to stay here and stand between you and lunch.
It seems like there's a general difficulty in finding non-trivial lower bounds on difficulty of all sorts of, even like multiplying pairs of numbers. Can you say anything about?
Well, the difficulty basically comes from the fact that there are an infinite number of possible algorithms. And all the ones we've thought of, and we've only thought of a finite possible number. We've only thought of a finite number of algorithms. We've thought of some really clever ones. So there must be some amazing. There could be some amazing clever algorithms out there. And to prove that there aren't any, you have to prove that no algorithm, now or in the future, no matter how big, is going to work. That's the basic. I think that's the basic heart of why we have two-dimensional problems, or other even simple lower bounds. And you're right, but then, not that we can't show SAT doesn't solve them all. We can't show SAT as in computable in linear time. I mean, state of knowledge is very well.
I was hoping there'd be an answer a little bit better than other infinitely many algorithms and having
A great one.
What's your favourite idea for separating P from P space?
Well, that's my favorite idea.
Yeah,
to me, I'm still a fan of diagonalization. I know direct diagonalization is not going to sell. The one I think might fall the first is logarithmic time, logarithmic space. That to me seems something that's plausible. And honestly, I think it's one of these things where you assume you get a collapse and you build collapses on top of it, and until you get so much collapsing that you can then do some sort of diagonalization. I'm still a fan of that kind of technique. So kind of hope that will work, but PMP space seems not that much easier than PMP. Thanks again.